welcome to day 23 of our 30-day coding challenge from CS and Math. And today I wanted to talk about algorithmic thinking as one of the pillars of computational thinking, and we're going to analyze the square rooting algorithm. This particular algorithm is going to validate a guess and check strategy, and really it's one thing I always just wondered about, like when I was using calculators when I was young, and I was like, okay, I understand a lot of this stuff, mental math, like how could I do this without a calculator, right? So I knew that I could do like the square root of 4, what times itself twice is equal to 4, well that's 2. But when I started thinking about, okay, well, what times itself twice is 2, that became very tricky, and I could get it by guessing and checking, and I could kind of go out one more decimal each time, but it was very time consuming, and I never really understood, like, how is this calculator doing this? And I eventually took a course. It was an edX course from MIT, from Professor Eric Grimson. And this is the course if you wanted to know and find it and maybe even take it. And this is his strategy. That's where I got it. I can't claim that I'm going to do it perfectly the way he did it because I didn't write it down. But I'm going to try to mimic what he said. So let's get set up in Trinket and get started. Okay, so I just commented out the title of this. We're going to call it the square rooting algorithm. We've talked about inputting stuff, so if I wanted to start this program, I could say my perfect square number is 16, hit enter. And so this is just going to prompt for user input. That's the input that I want to take the square root of, like I put into, let's say, Desmos or a calculator. And then I just want to initiate a variable guess. We'll initiate it at 0. So get that code set up. Okay, so what we're going to do here is use essentially a looping algorithm where we're going to just keep guessing at this thing, just like we would do like guess and check, like I said I tried to do when I was a kid. So let's do that with a while loop, because we can loop something until a condition is met. So while our guess squared, remember to get square, you use 2 multiplication, so this means square whatever the guess is. As long as that stays less than, in this case, remember I put in 16 for the perfect square. That value can change, but we're assigning it to the variable x. So, in the case that I put on Desmos the square root of 2, that would become x, right, if I put in 2. So we want to stay less than, when we square the guess, we want it to stay less than x. And then I'll put a semicolon. And essentially, we're just going to keep, while that's true, we're just going to keep incrementing the guess up. So let's just say we're going to take the guess and increment it plus equals. This is called reassignment because we assigned the guess to 0. Now we can say guess equals guess plus 1, right? But the shortcut we've used a bunch of times is plus equals 1. And let's just put a print statement in there that says, okay, this, by the way, will execute until this condition is met right here, this inequality. And once it's no longer less, it will break out of that loop. So let's go ahead and print guess. If we click run, and I'll type 16 in here again, and click enter. Notice that it's guessing 1 squared was less than x, 2 squared was less than x, 3 squared was less than x, but when it hit 4, 16 was x, right, and it broke out. So I could say, okay, well, the square root of 16 is 4. So get that functioning. I'm going to pause right now just to let you guys get caught up and think about that, let it sink in a little bit. Okay, so hopefully you kept trying some different numbers. If you were able to get this set up and wanted to test it, you'd be like, okay, well, does this work for guessing and checking like the square root of 9? Oh, it does. Does this work for guessing and checking the square root of even something like 100? And it does. Does it work for something that's not perfect square, like, 10? No, it does not, right? It can't comprehend that. It went past 3 because 3 was only 9, but then it went up to 4. Another thing you might notice is if you take the print out of the loop and do the print like this, and I do the square root of 16, that would just produce an answer 4. So I want you to think about how in the world could we make it so that we could do the square root of something not perfect? And think about that in your brain for a second. Well, in the edX course I took, Professor Grimson referred to this as epsilon. So he said if there's a small threshold, like you can change the threshold, and then I just searched this, got it on Wolfram Alpha, but essentially you want to approach some very infinitesimally small, possibly, quantity. So let's say, for example, we wanted a threshold of like 0.01. That could now become our guess increment. So essentially we could be like, oh, well, instead of 1, what if we just incremented it up by whatever we set the epsilon or threshold that we want it to be accurate to is. So just some very small value that we can increment up by. And notice now though, if we did something like that, let's say we even did, there. If I print the guess inside of it, let me just run a small one like the square root of 4. And if I run this now, well, that's going to take forever, right? But it does work. It seems to work. And if I took it outside of there, if it's not having to print the whole time, certainly I could run this and it would spit out the answer much faster. But then would this work for something, let's say, like we had talked about, like let's say the square root of 2, that was 1.41. And look, it's very close, right? 1.42. We could mess around with how to change that. And for example, I could make this 0.01. Let's try that again. If I say guess, and I'm going to do 2 square root of 2 again, 1.41. See, we're getting closer and closer, and the smaller you made this epsilon, the closer and closer you'd get to the real solution. And just to get that back up here, let me just go back to Desmos. Let me go back to my calculator. Type in the square root of 2, 1.414. So how close were we to that? Yeah, 4.3. So we're getting close here, right? And then if you wanted to, you could always just be like, all right, well, let's just round these things to the nearest tenth. I can do that right in the print statement. So I'm going to say round is a function, round that guess to, I don't know, 2 spots. Let's say 10 nearest 100th. So the second parameter here in that round function is how many spots you want to round to. So I could then run this and say the square root of 2. 1.41, right? If I wanted to do something big though, like let's say I wanted to find the square root of 90, and I run this, I would imagine this is going to take a while, right? So we don't want it to be clunky. We don't want it to take forever. I'm thinking this is still running. I didn't test this out before I was videoing it, but probably takes a long time, right, with that value in there. So we want to be thoughtful about what in the world are we going to do to make this efficient, right? Because we want to have something that's not clunky. All right, I paused there for a second so we weren't running in real time, just to check out. So that comes out to be 9.49, which it does in here. Just took a while to get there, right? It actually wasn't running when I was paused before, or rolling the screen before. I just had to rerun it. But how would we make this faster? How would we make this more efficient? And that's what we're going to talk about next. Okay, so I've changed a few things here. Take a glance through it and see if you notice what this code might do. Yeah, so we put not just a left starting value, but we've called the biggest the value could possibly be is x, right? Because if something times itself is equal to that number, it can't be bigger than that number, right? And then so what we're doing here for the guess is we're averaging, right? We're starting in the middle versus starting on the lower side, which should make things more efficient. I set the epsilon to start at 0.01, and I put another while loop here. Now, if you look at this while loop, so essentially, remember how we talked about guessing, right? If you square your guess, what times itself twice is equal to x. Well, this is saying subtract those and find the difference. If that difference is greater than or equal to the epsilon that we set, the threshold, then keep looping it. And this is just absolute value to keep it negative because it doesn't matter, or positive, I mean, just because it doesn't matter if it's too big or too small, right? It just matters about if it's greater than the threshold. So that is interesting thinking. Now what we could do inside of there still is put in some if-then conditionals like we did with the quadratic formula in yesterday's challenge. So take a glance at this code and see what you think that might do. Yeah, isn't this interesting? So if the guess squared right? If you square the guess, but that's less than what it's supposed to be, then use the left bound as your guess, right? Else, and this is what computers are really good at, by things that are things that only have two choices, biconditional, I guess. That's not the right word, but you know what I'm talking about. Only have two choices, binary. That's what I was looking for. Thank you. And yeah, it's setting the guess to the left lower bound. Otherwise, set it to the right higher bound. Then reassign the guess to that average. And once we break out of this condition, once we've got to threshold that we can break out of, print the guess. So let's try this. I know the video is getting a little long here, so I'll just put a 2 in there. Looks like it prints it out very quickly. We're not waiting. And for even example, if we do the 90 that we did before, prints it out very quickly and even more accurately. So hopefully this video got you thinking and you understood how this looping guess and check has a lot of value in math class. Thanks.